才可以写，对吧？这应该知道。
但是有时候写它上面就不会有那个红色的笔记，或者说你写右边，它出现在左边。
那这个我自己写起来是这样的感觉，那有点不太人性。
所以它现在是可以用的吗？
应该是可以。
好好好。
但就是操作上可能需要再习惯。
好好。Hello everyone. Today we will continue our discussion on section 8.2 to solve linear recurrence relations. So I hope you have studied section 8.1 because we have a lot of different applications for we can use linear recurrence relations to formulate this problem. And today we will see different types of recurrence relations and how to solve such different forms. For example, we have linear homogeneous recurrence relations or linear non-homogeneous recurrence relations. So today we will see different theories to help us find the solution of these relations. Okay, maybe last week we can see review the definition of recurrence relations again. Actually, recurrence relations is a sequence. If you can express an terms by the previous terms using one or more previous terms to express an, then that will be a recurrence relation. For example, we have seen Fibonacci number fn equals fn minus 1 plus fn minus 2. So we use fn minus 1 and plus fn minus 2 to express fn. So that will be one example we have studied before as a recurrence relation. And then we call a sequence is called a solution of that recurrence relation. Take Fibonacci number series again. We have 1, 1, 2, 3, 5, 8, 13, and so on. Then that will be a sequence. So that sequence is a solution for fn equals fn minus 1 plus fn minus 2. Okay, so then we have the initial conditions because once we need to discover what is F1, F2, F3, we need initial condition to help us discover what is F, for example, F0 or F1, then we can get F2 by the original definition of this relation. Okay, so today we are going to find a formula for the nth terms. In that case, you don't have to calculate F1, F2, F3 to F10 by a sequence. Once we have the closed form solution, then we can calculate F10 directly. For example, for Fibonacci sequence, what is the term F10? We don't know because we need to calculate what is F1, F2, F3, and then we can go to F10 to get the nth terms. But if we can find the formula or closed form formula directly, then we can use the closed form to that's the goal for this section. Let's see the definition of the first type of a recurrence relation. Linear homogeneous recurrence relation of degree k with constant coefficients. So that's a very long name, right? Okay, so let's see what are those keywords. So let's see the form of linear homogeneous recurrence relation. If we have an, we can write that equals C1 times A minus 1 plus C2 A minus 2 plus Ck times A minus K. Okay, so basically it follows the definition of a recurrence relation, right? Because an uses one or more previous terms to express an. So we use a minus 1, a minus 2, and a minus k. We use k previous terms to express an. So that's called degree k. Because we use previous k terms to express an. So that's what we call a recurrence relation of degree k. Okay, and then let's see what is constant coefficients. Because for each previous terms, we find some scalar, C1, C2, Ck, and these numbers are real numbers, so we call that constant coefficients. If the weighting factors for each terms, that is real number, we call this constant coefficients. So next, let's see another keywords. For example, what is linear? Okay, linear means the linear combination of an with an minus 1 and an minus 2. The power of these terms are 1. Okay, we don't have an minus 1 to the power of 2 to the power of 3. Okay, if we have the power more than 1, then that will not be linear homogeneous recurrence relation. Right? So we know what is linear and what is homogeneous. Homogeneous means we only use previous terms. A minus 1 to a minus k. We don't have other terms other than these previous terms. So if we have other terms to express an, that is not related to previous terms, such as a minus 1 to a minus k, then that will be non-homogeneous recurrence relation. So maybe we can see the example below. So if we have an equals to n minus 1 plus an minus 2 squared, so this concept is not linear homogeneous relation. It's not linear because we have a term with square here. Okay, so if you know in linear algebra, we call that linear combination. This is for each term with the power 1. If it goes with the power 2 or more, then it's not linear. Then let's see non-homogeneous. If an equals 3 times an minus 1 plus a squared. Okay, so now we know an with some terms is clear. It's not related to its previous terms. Okay, so this is not a homogeneous coefficient. Okay, for non-constant coefficient example, if the coefficient is some variable related to n, for example, n times a minus 1. Okay, so it's not a real number, so the coefficient is not a constant coefficient. Okay, so now let's go back to this definition again. Linear homogeneous recurrence relation. So when we have linear, then we have linear combination for previous terms, that is k. Homogeneous means we only have previous terms for this linear combination. And then we have constant coefficients for each previous term. Alright, Alright, so let's go back to our previous example, how to calculate the compound interest. So in this form, we have Pn equals 1.11 times Pn minus 1. So now you can see we only have previous terms, Pn minus 1 with the power 1. So that is linear. We don't have other terms other than previous terms. So it is homogeneous. And we have the coefficient 1.11. So it is constant coefficient. So we only use one previous term. So this is a recurrence relation with 1. For the Fibonacci number, we can see n equals n minus 1 plus n minus 2. So we use previous two terms. So we call this recurrence relation of degree 2. It's also linear homogeneous. Okay, now write down your answer. We have different choices from 1 to 6. Pick up the linear homogeneous recurrence relations with constant coefficients. So this is a multiple choice question. So select the correct answer from 1 to 6. Okay. Anyone want to share your answer with one extra point? Okay, please. 1 and 4 and 5. 1 and 5. Okay. So let's explain why the other answers are wrong. For example, 2. What's wrong with this recurrence relation? So 2 to the power of n. So how about 3? So it's not linear. How about 4? Okay, so we have plus 1 here. So we have some terms, it's not related to the previous terms. We only can use previous term minus 1, minus 2, minus k. But now we have a constant or scalar here. It's not related to the previous term. So it's not homogeneous. And how about 6? Okay, we have additional terms which is square, so it's also not homogeneous. Very good. Alright, now we have seen a lot of different examples of linear homogeneous representation. Now we want to discover what is the closed form formula for nth terms. Okay, so remember in section 8.1, we have the example of Tower of Hanoi. Once we have this linear homogeneous representation, we have plus 1 here. So how we discover the final solution? Okay, so we apply the substitution method, right? Because once we have Hn equals 2 times Hn minus 1 plus 1, then we can replace Hn minus 1 by this recurrence relation again, using 2 times Hn n minus 2 plus 1. Then we can apply this substitution in each step. In the end, we will have 2 of n minus 1. So I believe you have learned this process, but now I want you to notice something which is very important. Because if we have 2 times the previous term, for example, h n minus 1, then in this process, we are accumulating 2 times 2, 2 squared times 2, so n minus 1 times 2. So in the end, we have the term 2 to the power of n. Once we replace h0 by some real numbers, then we have something like 2 to the power of n. So by this observation, we have an important clue to solve with this recurrence relation, because our basic approach is to seek the solution. If we have an, then maybe the solution is something like r to the power of n. Just like our previous example, if we have the constant coefficient 2, then in the end, after multiple steps of substitution, it becomes 2 to the power of n. So maybe we can guess in this n recurrence relation, maybe its final answer or closed form is some constant r to the power of n. Okay, so maybe we can just write an equals r to the power of n as our final solution for the nth term of the recurrence relation. Once we assume the answer, then we can replace our original recurrence relation if we have a general form of non-homogeneous linear recurrence relation with degree of k. So in this case, we can see the general form is n minus 1 to n minus k times constant coefficients 1 to 6k. If we know an equals r to the power of n, then we can replace each terms by this solution. For an, we replace to r to the power of n. For an minus 1, we replace to r to the power of n minus 1. Right? So after we replace the original recurrence relation by our solution, then we can observe that we have Rn to the power of n minus 1 to Ra to the power of n minus k. So actually we can divide each term by r to the power of n minus k. Okay, so if we divide each term by this number, then the last term will be ck. Then the previous term will be c minus 1 times r. And then for our first term, Rn, if we divide by r to the power of n minus k, then it will be n minus parentheses n minus k, so that will be r to the power of k. So in the end, we will have an equation with only the variable r to some power k minus 2. Then we call this characteristic equation. Okay. Then for this characteristic equation, we can discover its solution. What is r? Okay. Next, we will see a very important fact. If we have a sequence n with the solution an equals r to the power of n, then we have sufficient and necessary condition if and only if r is the solution to the characteristic equation. Okay, so we give r a very special name, characteristic roots. Once we can discover the roots for this characteristic equation, then we will use it to solve our solution, because we assume n equals r to the power of n. Once we can discover what is r, then we are very close to our final solution of an. Alright, next let's see the theorem 1 to help us solve the solution of linear homogeneous recurrence relation. if we have C1, C2, which are real numbers, and then we have the characteristic equation r squared minus C1r minus C2 equals 0. So we know this is a quadratic equation. So we have assume we have two distinct roots, R1 and R2, for this equation. Then the solution to this recurrence relation An, we have the form An equals 1 times An minus 1 times C2 times An minus 2. Then we know if and only if the final closed form solution will be An equals another coefficient alpha 1 times the first root R1 to the power of N and plus alpha 2 times the second root R2 to the power of N. So this is a theorem. So once we can discover the characteristic equation, then we can solve what are those characteristic roots. And then we can apply theorem 1 to discover the final closed form solution. We can use R1 and R2 and this equation as our final closed form solution. So if you wonder why we can apply theorem 1, then we need to prove this theorem. So we must do two things to prove the fact. The first thing is we need to show that if R1 and R2 are the characteristic roots of the equation, and then we have two constant variables alpha 1 and alpha 2, then the sequence An, which is alpha 1 times R1 to the power of N plus alpha 2 times R2 to the power of N, which is the solution for this recurrence relation. Then we also need to show that every solution An of this recurrence relation, the original form is An equals 1 times this term, alpha N minus 1 is 2 times alpha. N minus 2 has An equals this solution as a solution. Okay, so maybe we can briefly review the step of proofs. How we prove we can use the characteristic roots as the final closed form equation. So the first thing we need to show that if An actually equals alpha 1 times R1 to the power of N plus alpha 2 times R2 to the power of N, then the sequence An is a solution of this recurrence relation. Okay, so actually we can apply the fact that R1 and R2 are the roots of the characteristic equation. So we can replace R1 and R2 in this equation as R1 squared equals C1 R1 plus C2. And also we can replace R2 in this equation as well. And then we can rewrite the original recurrence relation, C1 times A minus 1 plus C2 times A minus 2 by the facts we already know. Okay, now we have A minus 1, so we replace this term to alpha 1 R1 to the power of A minus 1 and alpha 2 times R2 to the power of A minus 1. And we can also replace A minus 2 in a very similar manner. And then by observing this equation, we can see actually we have something in common because we have something C1 R1 times something. We also have alpha 1 and R1 times something. So maybe we can combine the first term with the second terms by extracting the common factor alpha 1 and R1 to the power of N minus 2. So let's see for this term, if we move alpha 1 and R1 to the power n minus 2 out of this parentheses. And for the first terms, we only have 1 and R1 here. Alright? So let's consider the second term and the fourth term. If we remove the common term alpha 2 and R2 to the power of n minus 2. And for this term, we only have R2 times 1. Okay. And then for the fourth term, we have C2 here. And we move this out of the parentheses. Now we have C1 R1 plus C2. Actually, it's equals R1 squared because we already have the results of our characteristic roots. Okay, so we replace these two terms by R1 squared and R2 squared. So in this case, once we combine R1 squared times R1 to the power of n minus 2, then it will be R1 to the power of n. So now we have seen, actually this term is n, and we can verify it equals alpha times R1 to the power of n plus alpha 2 times R2 to the power of n. This is the proof for the first part. Okay, so for the second part, maybe you can look for more details in our textbook. Next, we will see how we apply this theorem to solve the proof form solution. Okay, so next let's see the example. What is the solution to the recurrence relation an equals a minus 1 plus 2 times a minus 2? With the initial condition A0 is 2 and A1 is 7. Okay, so remember, once we have the recurrence relation, we can replace an to r to the power of n. Okay, so for the original equation, we have r to the power of n equals r to the power of n minus 1 plus 2 times r to the power of n minus 2. Okay, so once we replace by r to the power of n, then we can divide by the common factor r to the power of n minus 2. Then for the left hand side, we have r squared. The right hand side, we have r plus 2. And when we move all terms to the left hand side, we have our characteristic equation r squared minus r minus 2 equals 0. Then we can find the roots of this equation. We have r1 equals 2 and r2 equals 1. Then we can apply theorem 1. Once we know these two characteristic roots, then we can rewrite an to some coefficient alpha 1 times first root to the power of n. So our first root is 2. So we use alpha 1 times 2 to the power of n plus alpha 2 times the second root minus 1 to the power of n. Okay, now we have only two unknown variables, alpha 1 and alpha 2. Then we can apply the initial condition to solve these two unknown variables. Because A0 is 2. So once we apply A equals 0, then we know A0 is 2. Then we have alpha 1 times 2 to the power of 0. So that will be alpha 1. And minus 1 to the power of 0 is 1. So the second term will be alpha. So we have alpha 1 plus alpha 2 equals 0. That's our first equation. And then we have our second initial equation, A1 equals 7. So we have step that equals 2 times alpha 1 minus alpha 2. Now we have two equations for two variables, alpha 1 and alpha 2. So we can solve alpha 1 equals 3 and alpha 2 equals -1. Then we replace this constant back to our equation. Now we know the n is alpha 1 is 3. 3 times 2 to the power of n. And then alpha 2 is -1. -1 to the power of n. So that will be our final solution. Okay. So now you need to know how to transform the original linear homogeneous recurrence relation into the characteristic equation, and then try to find the characteristic roots, and then apply theorem 1 to rewrite its solution, and then discover the unknown coefficients alpha 1 and alpha 2. Then we can find the final transform formula. All right, next let's see another example of our friend from large number. We already know this recurrence relation, and we know the initial condition is 0 if y is 1. Now we will write this recurrence relation equal to characteristic equation. So we know it applies to previous two terms. Right? So we can write r equals r squared equals r plus 1. Okay. So if you move these two terms to the right hand side, we have r squared minus r minus 1 equals 0. Then we can find the characteristic roots of r1 and r2. So now we can see these two roots are very ugly numbers. But never mind, because we can still apply theorem 1. So we have if n equals alpha 1 times r1 to the power of n plus alpha 2 times r2 to the power of n. Now we only need to apply two conditions to solve one is alpha 1 and alpha 2. Then in the end we can discover the corresponding solution to n. All right, any questions so far? Okay, if no question, then we will see another case. What happened when our solution has repeated roots? Okay, so because we assume in theorem 1 we have two distinct roots, R1 and R2. What happens if we have repeated roots with only R0? Okay, next let's move to theorem 2. If we have sequential real numbers for our recurrence relation, and we have the characteristic equation r squared minus 1r minus 2 equals 0, which has one repeated roots r 0. Okay, then our solution will be different because our solution becomes alpha 1 times r 0 to the alpha of n. So this is the same as 1, right? But for the second term, we have alpha 2 times n times r 0 to the power of n. So intuitively, consider in theorem 1, once we have two roots r1 and r2, we just use r1 to the power of n, r2 to the power of n here. But once n repeated roots are 0, then the first term remains the same, alpha 1 times r0 to the power of n. And for the second term, we have a very different value here because we need to times n, alpha 2, and r0 to the power of n as our second terms. Okay, so let's see the example. Okay, so what is the solution for the recurrence relation? N equals 6 times n minus 1 minus 9 times n minus 2. Okay, so we know it's a projective equation. So we can write r squared minus 6r plus 9 equals 0. Actually, we have the repeated roots 3. Okay, so our two roots are both 3. Okay, so by theorem 2, we need to write the solution. N equals alpha 1, 3 to the power of n, plus alpha 2 times n times 3 to the power of n as our solution. Then we use two initial conditions, a0 equals 1 and a1 equals 6, to discover what is alpha 1 and alpha 2. So if we know the difference between distinct roots and repeated roots, then we can apply theorem 1 and theorem 2. Then the following. All right, next we will come to the general form of previous two cases because we only consider previous two terms, which means the recurrence relation of degree 2. Now we go to theorem 3. If we have previous k terms, then our characteristic equation becomes r to the power k minus c1 times r to the power k minus 1 minus 0. And then if we assume we have k r1, r2 to rk, then we can rewrite our closed solution as an equals alpha 1 times r1 to the power of n, then alpha 2 times r2 to the power of n, to times alpha k times rk to the power of n. So if we make the same to our previous example figure 1, once we have two terms, we have r1 and r2. But if we have k distinct roots, we just add more terms here in our solution. Okay, so that will be easy. Let's see the general case of repeated roots. Okay, if we have C1, C2 to Ck as our coefficients, so our characteristic equation r to the power of k. Okay, then we have the same characteristic equation as theorem 3. But now we have distinct roots r1, r2 to rk with the multiplicity n1 and 2 respectively. And we know n1 plus n2 to nt equals k. Okay, so maybe we can have an example to help you understand what are these notations. Let's see this example. Okay, if we have the characteristic roots 2, 2, 2, 5, 5, 9. Okay, that means we have 3 roots, but multiplicity of each root, it repeats 3 times, 2 times, and 1 times. Okay, so maybe you can relate it to the notation here. Once we have repeated roots, so we have t roots, not k, because theorem 3, if the leading term is r to the power of k, then we will have k distinct roots. But now we have repeated roots. So some repeat 3 times, some repeat 2 times, then totally we will have t distinct roots, r1 to rt, just like our previous example, 999552. In that case, we have 3 distinct roots. And the multiplicity of each root is 1 and 2, 3 and t. So back to our previous example, 999, the repeating number is 3. So the multiplicity for 3 roots will be 3, 2, 1. Okay. And we know n1 plus n2 plus n3 to n t Okay, so now we can see what is the general form of repeating roots in this case. Okay, we have a n equals previous terms by homogeneous recurrence relations. Then the solution will be okay, our first roots are 1. Actually, it's repeated n times, right? So if it repeats twice, in our previous discussion, we have alpha plus alpha 2 times n times 1 to the power of n. Right? That's the case for 2 repeated roots. However, if the multiplicity is 1, then we will have alpha 1 times n times alpha 1 2 times n squared and alpha n1 minus 1 times n to the power of n1 minus 1. Okay, we will have more terms. So if the repeating number is 2, then we will have 2 terms. However, if the multiplicity is 1, then we will have a 1 terms for the repeating roots of 1. Okay, so it follows for R2, R3 to RT. So it depends on M1, M2 to MT. What's the number of multiplicities? Okay, so let's see the example here. Okay, if we have the 222,559, so we know it repeats 3 times, 2 times, and 1 time. So the general solution will be if we consider the first roots 2. So we have 3 terms. So we can use the index to indicate one is we use 1 to indicate is the first root. And we use 0, 1, 2 to indicate different terms for the same root 2. Okay, so we have alpha 1, 0 times plus alpha 1, 1 times n, and alpha 1, 2 times n squared. If we repeat 3 times, then we will have 3 terms for the roots 2. And then for 5, it only repeated twice. So back to our previous scenario 2, we have alpha 2, 0 plus alpha 2, 1 times n times 5 to the power of n. So if it is just repeat once, then we have alpha 3, 0 times 9 to the power of n. And that will be our general solution. Okay, so let's jump to the next example. If n equals minus 3 times a minus 1, minus 3 times a minus 2, minus a minus 3. Okay, so we know it applies 3 previous terms. So our characteristic equation will be r to the power of 3 plus 3 times r squared plus 3r plus 1. And we know we have the single roots minus 1 in this equation, and the multiplicity is 3. Okay, so if we have roots of the multiplicity 3, then we will have 3 terms alpha 1, 0, alpha 1, 1, n, alpha 1, 2, n squared times minus 1 to the power of n. And we can use 3 initial conditions to solve the unknown variable alpha 1, 0, alpha 1, 1, and alpha 1, 2. Alright, that's all for linear homogeneous recurrence relation. How to discover its closed solution for an terms. Alright, any question here? Alright, if no question, then we will see the second category, linear non-homogeneous recurrence relation. So now I want you to distinguish the type of the problem because we combine different keywords, linear, non-homogeneous. Okay, so that means an expressed by previous terms in a linear combination fashion, but we have more terms that is not related to previous term a minus 1, a minus 2. So let's see the definition. A linear non-homogeneous recurrence relation is constant coefficient. It's a recurrence relation of the form c1 times a minus 1 plus c2 times a minus 2. But we have something different in the end. We can write f of n. That is a function of n by different forms. For example, f of n can be 2 to the power of n. It can be n cubic in other forms related to n. So generally, we can just write f of n instead. Okay? And then to discover the solution, actually, we can partition this equation to two part because we have discussed how to discuss the solution of linear homogeneous difference relation. So basically, this part is linear homogeneous difference relation. And we have the second part here, which is non-homogeneous part. Okay. Next, let's see some examples you may see in your homework assignment or final examination to discover the solution of this linear non-homogeneous recurrence relation with the form f of n equals 2 to the power of n, or n squared plus n plus 1, or n times 3 to the power of n, or factorial of n. Okay, you can consider all of these are the functions of f of n. Okay, but once we separate the linear homogeneous part from this equation, then for the first equation, the linear homogeneous part is n equals n minus 1. And for the second equation, we have n equals n minus 1 plus n minus 2. So that's our best linear homogeneous recurrence relation. All right, so next we will see what is theorem 5 to help us discover the solution for linear non-homogeneous recurrence relation. Okay, so we consider ANP as a particular solution of non-homogeneous linear recurrence relation. Okay, and then we consider our solution ANH as the solution of linear homogeneous recurrence relation. Because we just mentioned that we can consider AN as two different parts, the linear homogeneous part and non-homogeneous part. So we can separate our solution to ANH, a particular solution for f of n, and the solution ANH for linear homogeneous recurrence relation. Okay, so ANH is what we call associated homogeneous recurrence relation by the following equation. So we have seen this in our previous theorem. Next, let's see this example. Find all solutions of a recurrence relation AN equals 3 times n minus 1 plus 2n with the initial condition A1 equals 3. All right, so clearly this is a linear non-homogeneous recurrence relation. It's just use previous terms A minus 1 with f of n equals 2n. Okay. So let's see. We can discover the solution of ANH by our previous method. because for our characteristic equation, we have r equals 3, right? So our roots will be 3. So we can write the homogeneous solution h by alpha times 3 to the power of n. Okay, so that's our solution for homogeneous recurrence relation. Let's consider the particular solution because we have the second part f of n equals 2 times n. So it's a polynomial function of n degree where the degree is 1. Okay. So if we have the polynomial function with the leading term is degree 1, then we can write its general form by Cn plus d. Because Cn plus d is a polynomial function with the leading term n to the power of 1 and with the constant terms. Okay. Then we can apply initial conditions to discover what Cn because we already know Pn equals Cn plus d. So now we have our solution. N equals 3n minus 1 plus 2n. Where we have Cn plus d equals 3 times c times n minus 1 plus d plus 2n. Okay, once we replace an by Cn plus d, so in our left hand side, an becomes Cn plus d. In our right hand side, an minus 1 becomes c times n minus 1 plus d. And we have the last term 2n. Alright, then we can move all terms with n together in the other coefficients. So we have 2 plus 2c times n plus 2d times 3c equals 0. Okay, so now we know Cn plus d is a solution of this equation if this term and this term are 0. Now we have two equations for the unknown variables c and d, and we know c is minus 1 and d is minus 3 divided by 2. So this is our particular solution in of p equals cn minus d. So it will be minus n minus 3 divided by 2. Okay, so this is our particular solution. And we already have our homogeneous solution, alpha times 3 to the power of n. So now we can combine this part together. Actually, our an equals plus h. So this gives us our this equation. In this equation, we have the unknown variable alpha, so we can apply initial condition again. If a1 equals 3, then when n is 1, so we can discover the solution. Alpha equals 11 divided by 6. Okay, so our final closed-form solution will be an equals minus n minus 3 divided by 2 plus 11 divided by 6 times 3n. That's our solution. Okay, so maybe we can use this example and check this theorem 5 again. Once we have a linear non-homogeneous recurrence relation with the homogeneous part and non-homogeneous part, we can apply theorem 1, previous theorem, to help us discover the solution of homogeneous part in H. And then we also need to discover the particular solution in P for the problem of n. And the solution will be ANP plus AH. Then we just need to discover what are those coefficients, alpha 1, alpha 2, are applying the initial condition, then we can discover the final closed-form solution. Alright, so our last example is nonlinear, non-homogeneous recurrence relation. So you can see by this example, we have an squared minus 2 times n minus 1 squared equals 1. Okay, so in this, you can see when we express an, actually we use the previous n minus 1, but we have a square here. And we also have 1 here. Okay, so it is non-linear, non-homogeneous recurrence relation. So lastly, let's see how to solve this very particular recurrence relation. Okay, because it is non-linear, so maybe we can use a variable bn. If we write bn equals a squared instead, then we can rewrite this equation to a linear recurrence relation. Because bn equals a squared. So let's see what we can write the original recurrence relation. So now we have an squared by bn. 2 times n minus 1 squared, it will be 2 times cn minus 1 equals 1. Now we rewrite by this formula. It becomes linear non-homogeneous relation, right? If we can rewrite to linear non-homogeneous relation, then we can apply theorem 5 again to discover the solution of a pure solution in homogeneous solution in H. So let's see the next step. Once we have this equation, then we know the characteristic roots is 2, right? R minus 2 equals 0 as our homogeneous solution. So we can write ANH alpha times 2 to the power of n. Okay, so this is the homogeneous solution. Then for particular solution, we can see actually the non-homogeneous part is 1. Okay, so the general form of 1 together, we can write C instead. Okay, so because C means the number can be either real numbers. Okay, then our solution will be Bn equals alpha times 2 to the power of n plus c. So remember, this is homogeneous solution. This is particular solution. Okay, next we can apply the initial condition B0 equals 1 and B1 equals 3. Then we can have two equations, alpha plus c equals 1 and 2 alpha plus c equals 3. Then we just discover what is the coefficient alpha and c. All right, and then we can derive Bn equals 2 times 2 to the power n minus 1. Okay, so that will be 2 to the power n minus 1 minus 1, or n plus 1 minus 1. Okay, so that will be the answer or total solution for Bn. But remember, our original equation is Bn. So when we write Bn equals a squared, okay, then we will have a squared equals 2 to the power of n plus 1 minus 1. So in the end, when we write to n, then that will be n equals the square root of 2 to the power of n plus 1 minus 1. Okay, the last thing you need to be very careful because you need to verify when we have an squared equals something, actually we have positive right minus square root of something. Okay. And when we consider an equals negative square root of Pn, then when we have alpha 1 equals 0, our initial condition, so the minus square root of Pn is not a possible solution. Okay, so our final solution will be An equals positive square root of 2 to the power of n plus 1 minus 1. Right, so any question for the last part? All right, so I would like to invite someone to summarize the process, how to discover the closed-form solution for linear homogeneous recurrence relation, linear non-homogeneous recurrence relation, and nonlinear non-homogeneous linear recurrence relation for us in Chinese. Okay, briefly introduce the steps how to discover the solution for 3 different types of recurrence relation in Chinese and summarize for everyone. Anyone? All right, maybe when I put 3 different questions together, it will be too difficult. So maybe we consider one by one. Okay. Firstly, how to discover the closed solution for linear homogeneous recurrence relation. Anyone can summarize the process for us in Chinese? All right.嗯嗯，好。那假设你的 recurrence relation 它不只有2项，它有10项。嗯嗯好，非常棒，哈。那要不要试试看？接下来如果是 linear 的 non-homogeneous recurrence relation 怎么办？嗯嗯嗯嗯，那 ANP 要怎么给啊？嗯，OK，我们这个例子是 3an 减1加 2n，那它的 ANP 要怎么给？对， 我想吃。
对，我想吃，
嗯
然后那个 C N 加
嗯，
然后再丢进去原本的式子里面，然后因为homogeneous 的写完都是几根在一边嘛，也很难讲，但就单纯把那个2跟那个 C N 加丢进去，它也会符合那个递回的关系。
就可以解。
对，也可以解出那个 C 跟 D 的形状。
好，那我问你哦，假设这边是10n平方，
应该是设 n C n 平加 D N 加 E。
对，好，非常好。好，那最后假设是 nonlinear 的 non-homogeneous recurrence relation 呢？
先把那个linear 的日体方系数可以设成第一个就是一个新的数列，然后它这个比较小掉，这个形式就变成一撇的动态，然后再用前面就是它只是 homogeneous。
好，太好了，好，真的很棒，好，那个加1分，好，没问题啊，好。那我们最后呢，再开放同学们一个加分的机会，好吗？但是let's see our homework assignment. We have 2 questions for each section. So I hope you can do this exercise because we have a lot of need to practice. Okay, so it's still 2 weeks for the due day. And we have 2 minutes, so maybe I can give you 1 extra point. So please write down your solution for this one. But now I want you to apply substitution methods to discover the solution of this recurrence relation. Please try to find your answer. Not using the method, but using the substitution method. Okay, let's see. Because when you have the final exam or maybe the entrance exam of master's degree, you don't have to apply one substitution method. If you see n squared minus 2a minus 1 squared, maybe you don't have to use this method. You can just simply apply substitution method, and you can discover the solution. So let's try to use substitution method. If you forget, we have our previous example of Tower of Hanoi. So just replace the term Hn, Hn minus 1, Hn minus 2 by the previous terms. And in the end, you will have something 2 to the power of n minus 1. Okay, so now we just replace this recurrence relation by an squared equals what is 2 times an minus 1 squared plus 1, right? Equals 1. Alright, when you finish your answer, then you can hand your paper to TA and you can leave the classroom. Alright, see you next, 2 days later.